So I talked about doing more examples today, which is what we're doing. I specifically said we'd be doing more complicated examples. I'm not sure if that's true, but there are some pretty standard stuff we should do. So let's just look at a few more of these. In particular, I can't remember yesterday exactly what comparisons we made, so some of these will probably be pretty similar to the stuff we've done. But let's look at 1 over 3 to the n plus n. And I want to say we did something like this yesterday. So, or maybe not, I'm not sure. Does anybody sort of want to give me a guess whether this converges or diverges?
Probably converges.
Converges is correct because, and this is intuition that we're hopefully developing is going to be really important tomorrow. Your intuition should be that that n is big and 3 to the n is exponential. It's getting unimaginably large very quickly. Like if you compare 3 to the 100th power versus 100, that 100 might as well not be there. So this looks a lot, by that logic, like 1 over 3 to the n, and this doesn't look quite like anything until you realize that you can rewrite it as 1/3 to the power of n. And 1/3 to the power of n is a geometric series that r is less than 1, it's 1/3. So 1/3 to the n converges. So we're going into this hopefully with some kind of intuition. And a downside of the limit comparison test is that we can't leverage this intuition directly. Like, we can't just say, okay, this looks like a convergent series, so it converges. We have to say, it looks like a convergent series, so we think it converges. So if we want to use the limit comparison test, we need to find a bigger convergent series. And then we have to sort of mess around with this. We've seen that the comparison test can be very delicate, like whether you have addition or subtraction here isn't really affecting our intuition, but it greatly affects how the comparison test is going to work. Here we have addition, which turns out to be kind of the nicer one, because to make this bigger, well, there are a bunch of things we could do. But we don't just want to make it bigger, we want to make it bigger and convergent. And I'm going to tell you that, most of the time, most of the time when you're using the comparison test, you're trying to compare to either a p-series or a geometric series, because those are two series where we know whether they converge or not. So, I mean, if we want to make this bigger, we could, if we replaced that 1 with almost anything, the natural log of n is bigger than 1. So we are making this fraction bigger, but this is probably not where we want to go. We're probably trying to compare to a geometric series or a p-series. This natural log, we don't know what to do with it. We don't know whether this series converges or not. So our options, if we're trying to grow with this, are to increase the top, increase 1, or decrease the bottom. And again, we have to do this in an artistic way. Because one way we could decrease 3n plus n is to get rid of that 3n. I mean, that certainly makes it smaller, but this is useless to us because 1 over n is not convergent. 1 over n is the harmonic series. It diverges. Being less than infinity isn't telling us anything. So we can increase it in that way, but it's not productive. It's not useful. Whereas, I mean, if we cross out this plus n, that decreases it, certainly. Heck is Shadron's state texting us for? It's a test, some kind of tornado drill. So this is true, and this is useful. 1 over 3 to the n is the geometric series. 1 over 3 to the n is convergent. It's finite. So we are less than this finite thing. So this converges. And as I say, I mean, this test is delicate. In the sense that if instead of addition, we had subtraction, I mean, that doesn't really change our intuition. We still think this looks basically like a geometric series. We think it probably converges. But now we can't just cross off the n, because crossing off the n increases the denominator. It makes it go in the wrong direction. And sometimes you can try to be clever or do something cute. Most of the time, I'll say this, most of the time, if there's not a very obvious comparison to make, it's probably a sign that you want to try a different test. There are ways to deal with 1 over 3 to the n minus n that are not going to be a headache. So that's an example. Let's do an example where we compare to a P series. Let's look at that. And I mean, as far as what we do here, I've sort of given it away. I mean, I've said we want to compare it to a P series. A P series is 1 over n to a power. So if we look at that, we see a 1 over n cubed. That's presumably the P series we want. It's a similar intuition to what happened back here. I mean, n cubed is obviously not as fast growing as an exponential, but still, I mean, when n is 1,000, n cubed will be a billion. A billion is much larger than 1,000. So we think when we look at this series, we think, well, the n cubed, that's the really important part. That 3n, that 1, neither of those are doing much compared to the n cubed. And 1 over n cubed is a P series, and it converges. P series are sort of the opposite of geometric series. For a geometric series to converge, something has to be less than 1. For a P series to converge, something has to be greater than 1. 3 is greater than 1. So we think this probably converges. But again, the weakness of the comparison test is that we can't directly use that intuition. We can't say, well, this looks like 1 over n cubed, and n cubed converges, so this also converges. We have to say, well, if we're going to use the comparison test, we need to show that this is less than a convergent series. And once we've reached this point, this is very similar to the previous example. Going to be a certain amount of repetitiveness in these examples to increase a fraction. Well, we could increase the top. We could increase 1, but I mean, increase it to what? I mean, there is nothing that's springing out to me here as being very useful to do. Conversely, we could try decreasing the denominator, and again, the question arises, decrease it to what? But here we can decrease this in what I hope is a pretty natural way. It's basically just how we handled the last example. How can we decrease this to get a convergent series?
Just get rid of the 3n plus 1.
Get rid of the 3n plus 1. And again, this is very delicate. If instead of addition here, we had subtraction, we couldn't just get rid of the subtraction because getting rid of subtraction is going in the wrong way. But because everything is being added, if we just start crossing stuff out, we are decreasing it. And decreasing the denominator increases the fraction, and this is exactly what we need. This is convergent. I mean, I guess if I'm talking about convergence, I properly ought to have the sigma symbol written on the board, but you know what I mean. The sum of 1 over n cubed is convergent, so the sum over this cubic polynomial is less than a finite thing. It converges. Let's do maybe 2 more examples. That will end up leaving class a little early, but I do think there's a limit to how many examples you can show before the student sort of starts to choke on them. We've been messing around. I think that all of the examples we've done, both today and yesterday, were messing around with denominators. So let's do a quick example where we mess around with the numerator. And let's look at the natural log of n over n. And we don't necessarily have a huge amount of intuition here. The natural log of n is a very slow growing function. We do know that, the natural log of e to the 1000th power, e to the 1000th is unspeakably large, atoms in the universe type scale. 1000 is nothing compared to that. So it is very slow growing. We know that 1 over n diverges. We know that's harmonic. Our guess, now I say our guess as if I didn't write the problem, but a reasonable guess would be that maybe this diverges. The natural log of n grows so slow that maybe we can just sort of ignore it. And if we could just sort of ignore it, that would leave us with the harmonic series. It would leave us with something that diverges. So a lot more tentatively than the last 2 examples where I was really confident. This looks like this looks like that, but we're going to guess that maybe this diverges. And if we want to show that something diverges using the comparison test, we need a smaller divergent series. We need to be bigger than infinity. So to shrink this, there's some combination of those two things. To shrink a fraction, you either make the top bigger or the bottom other way around. To shrink a fraction, you either make the top smaller or the bottom bigger. And I mean, there's a bunch of things we could do to n that would make it bigger, but really the natural log is the problem here, right? I mean, like if we turn n to n cubed, well, now we have the natural log of n cubed. What's that? Is that convergent? Is that divergent? It's hard to say much about. So we can sort of accomplish a few things in a single step. That natural log is messy. We'd like to replace it with something nice. Well, a natural log is certainly bigger than 1. It's, it's the natural log eventually is bigger than 1. I mean, the natural log of 1 is 0. The natural log of 2 is probably less than 1. We don't have to worry about that. It's a theorem of convergence that we can start wherever we want and not affect the convergence of the series. So if we start a little on, then the natural log is greater than 1. And we can write these inequalities. 1 over n is harmonic. 1 over n diverges. So we have exactly what we need. This is bigger than something that is infinite. It's bigger than infinity. Bigger than infinity means you're infinite yourself. That's, okay. I said one more example. We'll make this slightly more intricate. E to the negative n over n plus the cosine squared of n. Let's do 2 more examples. I keep meaning to do something involving factorials. Let's do an example that involves the factorials. But back to this. Do we have any intuition about this? I think this is written in a way that maybe obscures the intuition we ought to have, which is that e to the negative n is putting an exponential in the denominator. A negative power goes into the denominator. And 1 over e to the n, this certainly converges. It's a geometric series. So that e to the n is tending towards convergence. And then you're taking something that's already trying to converge, And you're making it even smaller. You know, you're taking something that's already converging and dividing it by some very big number. Remember that the cosine squared is stuck between -1 and 1. So, you know, a billion plus the cosine squared is about a billion. So, if we're taking something that we think is already probably finite, and we're making it even smaller, well, this whole thing should probably be finite. And once we've come to that guess, or guess is underselling it, maybe. It's a pretty firm argument, but let's see if we can make it really firm using the comparison test. And if we think that this is probably finite, and we want to be using the comparison test, we want to make this less than a finite number. So we want to make it bigger. And I mean, the way we make it bigger is probably pretty natural at this point. But I'll still talk a little about it. If these are our options, I mean, the way I phrased it, and I know it can be sort of, I've done this many times before. I mean, I don't expect you to see that e to the n and say, oh, well, bet this converges, but that's the intuition we are working towards. Because this e to the n is the reason that I think this series converges, I probably want to leave it alone. You know, if I'm trying to get a finite series at the end of the day, I don't want to do anything to this e to the n that might break the convergence and make the whole thing infinite. So this n over the cosine squared of n, we can decrease this in a pretty serious way. Obviously, we can't just literally cross everything out. We don't want a division by zero error. But n is greater than 1. And then if we get rid of addition, that will shrink it further. So we can just take the denominator and shrink it down to 1. And usually that doesn't work. Usually if you shrink the denominator down to 1, you're going to wind up with a divergent series and the comparison test is going to fail. It's because this e to the n is doing such a job of causing this to converge that we're able to go so far with the denominator. And e to the negative n, I erase this, but that's 1 over e to the n. And I think this can be confusing because it looks a little like a p series, but you know, 1 is 1 to the n. So this whole thing is 1 over e to the n. 1 over e is less than 1. This is a convergent geometric series. Again, going back to the pickiness of this test, this cosine squared that looks as if it's making this thing more complicated is actually making it less complicated. It's making it easier. And if we just had the cosine, it's not at all clear how we would proceed because the cosine can be positive or it can be negative depending on what n is. So 1 plus the cosine of n isn't necessarily bigger than 1. Sometimes it's bigger than 1, sometimes it's less than 1. You can't then replace this with 1, and it's not clear where you would go. Probably where you would go is using something other than the comparison test, although offhand I'm not immediately clear what else you would use. Let's see, I don't know if the comparison test is going to give us what we want here, but I think we can finagle it. Let's look at 1 over n factorial. We probably, I mean, if we've maybe seen the factorial in like a probability class, we don't probably have a lot of intuition about this. So I'll share the intuition we should have, which is that the factorial grows really quickly. It's not quite, or is it? Is it even bigger than exponential? I need to think about that. But like, it's growing really quickly. The denominator in that fraction is really big. That causes the fraction itself to be really small. I think that this converges. But can I show that it converges? Well, to show that it converges, I need a bigger convergent series. And it's usually the case. I mean, I won't say always, but if we just have a constant, there's probably not a lot we can do with that. Probably increasing 1 is not viable. And we decrease n factorial. I mean, we obviously can, and factorial is super big. Can we decrease it in a useful way that gets us a convergent series? Remember, we're trying to increase this fraction, but not increase it too much. We want this to be convergent. And we can do that, not in a way that's probably immediately obvious, but let's look at 5 factorial, for example. 5 factorial is 5 times 4 times 3 times 2 times 1. And as far as making this smaller, if I make the 5 smaller, or if I make the 4 smaller, or if I make the 3 smaller, any of those would shrink the factorial. And this is a famous trick. It's not something you would necessarily come up with on your own. But if we shrink all of these down to 2, we could increase 1 as well. Increasing 1 makes this a little bigger, but going from 5 to 2 makes this much smaller. So it evens out to an increase. Is 2 to the 5th, in general, n factorial is bigger than 2 to the n. And with that, it's a trick, but with that trick, we can decrease the bottom and increase the fraction if we replace that n factorial with a 2 to the n. And then this is 1 over 2 to the n, and 1 over 2 to the n is finite. It's a geometric series. R is less than 1. So the comparison test applied in a kind of cute or a kind of clever way gives us the convergence of 1 over n factorial. And that's important. I've mentioned this before, but the primary application of sequences and series involves a factorial term. So we need to be developing some intuition about how factorials work. And here is our first piece of intuition. The factorial grows really quickly. It is in fact bigger than that exponential. It's bigger than 1/2 to, it's bigger than 2 to the n. So because it grows so quickly, you put it in the denominator and you're getting something really small. And you're getting something so small that even though you're adding infinite terms together, the result converges. And that is that. There are sometimes, at this point, we don't have a lot of options. It's sometimes possible to study convergence or divergence in more than one way. So here, we had e to the negative n, and I said, oh, this is a geometric series. It converges. You could also, going back to a problem from the test, you could also approach it using the integral test. If you take the integral of that, you'll find that it's finite, so you can approach it that way. And a number of problems that we did today could also be done using a somewhat related test called the limit comparison test. We'll cover that tomorrow, and I will see you then.